Hello everyone, I am Prajwal Agarwal and today we are going to discuss this problem tree upshot. This problem is rated as easy medium on CodeChef and you require the use of DP, DFS and trees to solve this. This problem was recently asked in October lunchtime. So guys, if you haven't read the problem yet, go back and read it, try it out and then come back and see the solution. With this, let's begin. In this question, we are given a tree with n nodes. So let us take this example tree as to understand the problem. Now it is given that the node with index 1 is the root of the tree. And our task in this question is to assign color to each node. The color can be either black or it can be white. So given n nodes, we need to assign either black color or white color to all the nodes. Now there are some terminologies to understand. So we define W of I as the number of white nodes from the simple path from the root node till I. So for understanding, let's color the nodes of the tree. We will do this randomly for now. So let us say that this is black, this is white, this is black, and this is again black, and this is white. So now W of I is the number of white nodes from the simple path from root to I. So let us take the example of this node 4. So W of 4 is equal to 1. Why? Because in the simple path, which is 1, 2 and 4, only node 2 is colored white. So the number is just 1. Similarly, we will define B of I as the number of black nodes from the simple path from 1 to I. So again, taking the example of node 4, B of 4 is in this case 2, because root node 1 and the 4 itself is colored black. We can take any other example. For example, B of 3 is just 2, B of 5 is just 1. Now we define the cost of each node I. So the cost of node I is basically the absolute difference between the number of white nodes and the number of black nodes in the path, in the simple path from root node till that node I. So for example, taking the node 4, the cost of node 4 is equal to the absolute difference between the number of white nodes, which is equal to 1, and the black node, which is equal to 2 in the simple path. So it is equal to W of 4 minus B of 4 equal to 1. For root node, it is equal to 1. For this node, since we have 1 white and 1 black, this is equal to 0. For node 3, we have 2 black nodes and no white node. So it is equal to 2. And for this node 5, we have 2 white nodes and 1 black node. So we have 1. Now we have to define the cost of tree as the summation of cost of all the node I. So it is equal to summation of I is equal to 1 to n and cost of node I. So for example, in this tree, the cost of tree is equal to the cost of node 1, which is 1 plus 0 plus 2 plus 1 plus 1. This is equal to 5. Now we have to define the value of tree. And this is just simply equal to the absolute difference between the total number of white nodes and the total number of black nodes. So this is for the whole tree, hence we can just count. So the number of black nodes are 1, 2 and 3 and the number of white nodes are just 2. So the value of tree is 1. Now in the problem we will be given a single query queue which can be either 1 or 2. Basically we have to assign color to this tree such that our first priority is to minimize the cost of the tree. And after minimizing the cost of the tree, we have to find the maximum value or the minimum value depending upon the value of q. Basically, how we attach colors to these nodes, either black or white, will actually affect the cost. So we have to assign colors first such that the cost is minimized as well as we get the maximum value of the tree or the minimum value depending upon q. We have to output this minimum and maximum value accordingly. In the constraints, we are given test cases from 1 to 1000. The number of nodes can be from 1 to 10 to the power 5. q can be 1 or 2, and we will be given edges in the form of u to v, which is 1 based indexing. Now let's look at some test cases to better understand the problem. In the first test case, we are given this tree. Now we are given q as 1, so we need to find the maximum value of this tree. So to do this, we have to first assign the black or white. We will denote white with 0 and black with 1. So let us say that we color the node 1 as 0, which is white, and we color all these nodes as 1, which is black. So first we find the cost. To find the cost of the tree, we have to find the cost of each node. So for node 1, it is equal to 1 plus, for node 2 and 3, we have same number of white and black node in this simple path. So this is equal to 0 plus 0. For node 4 and 5, we have 2 black nodes and 1 white node. So the difference is 1. So we have 1 for 4 and 1 for 5. So the total cost we get is 3. Now the value is defined as the absolute difference between the total number of white and black nodes in this whole tree. This is equal to white node, which is 1, and black node, which is 4, equal to 3, as given in the output. So guys, you can try coloring this node in any other way, and the minimum cost that you can get is actually 3. This is the configuration that will give us the maximum value, which is also 3. Now in the second test case, we are given kind of the same tree, but the query is different. We are given 2. So in this case, we have to minimize the value of the tree. So to do this, we can assign white to first node, and then we can assign black to 2 and 3, and now we again assign white. So now as you can see, if we calculate the cost, so for node 1 it is again 1. For node 2 and 3 it is both 0, because we have same number of white and black node in this path. 0 plus 0. Now we have for node 4 as 2 white nodes and 1 black node. So the difference is 1. And similarly for node 5 the difference is 1. So as you can see that the cost is 3 again, because the tree is same. And the value now we get is the difference between the white and black nodes. This is equal to 3 minus 2 equals 1, as given in the output. Now let's move on to the approach. So basically in this question, we are given a tree with n nodes. We have to assign each node a color, black or white. So as stated before, we will use 1 for black color and 0 for white color. Now we have defined cost of tree as the summation of cost of nodes, and the value of tree is equal to the difference of white and black nodes, and we will take the absolute value. Now to answer the queries, our first priority is to minimize the cost of this tree. So we have to first minimize the cost, for which we need to assign the coloring. So now to solve problems like these, we have to approach them using some observation. In questions like these, there are always an observation that you need to notice first, and this can be achieved by first trying out some test cases, and after that you'll try to see some pattern, and similarly you will move towards the solution. So in this case, first of all, it does not matter whether we assign white color or black color to the first node. Because we are taking absolute value, it does not matter. So let us say that we take black. So our first node is always black. Now, if we assign nodes 2 and 3 again black, then we know that the cost of node 1 is 1, and this cannot change. But cost of node 2 and 3 depends upon their assignment. So let us say that we assign black. In that case, both these costs will be equal to 2, hence our cost will increase. But if we had assigned white, then we can see that the new cost is equal to 0 for nodes 2 and 3. And this is optimal. This is because the number of white nodes and black node in the simple path is same, so the difference is 0. Now the other important observation is that the contribution of 1 and 2 to its children 4 and 5 is 0. So actually we can say that these nodes do not contribute anything to the cost for nodes of its children starting from level 3. So these subtrees 4, 5 and with 2 children 6 and 7, these actually act as individual subproblems, and if we minimize their cost, then we will minimize the cost of this whole tree. Now these subtrees actually do not have a relation with one another. It does not matter whether we assign black or white to 4, it is not going to affect 5. Also, the contribution from above is 0, hence these can be treated as individual subproblems. So now 4 becomes the root node of its own subtree and 5 becomes the root node of its own subtree. For root node, we know that we can assign anything because we are taking the absolute values and the contribution from above is 0. So we will, let's say we assign white and the cost is 1. And for this also we assign white, the cost is 1. For even levels, which is 6 and 7, we are not going to assign white, because if we do, then the cost will become 2 and this is not optimal. We could have assigned black and the cost would have remained less. And since we need to minimize the cost, we will assign black. So this is pretty much fixed. So the cost is now 0 for 6 and 7. Now, I hope you can see the repetitive pattern that we have. The pattern is for every odd level, we have a cost 1. And for every even level, if we flip the color, we have the cost 0. And the contribution from above is 0 to every odd level. So these can be treated as individual subproblems. Let us say that we had some node here. Then we would have divided these nodes into individual subproblems and tried to solve them. Basically, the cost here is black, white, due to which the contribution becomes 0 to these nodes, to the nodes at odd level. So we can treat them as individual subproblems. Now to answer the queries, let's define a vector v. We will define this vector v for every node present at the odd level. Basically, it will store the number of parents and the number of children for every node present at the odd level. Basically, this signifies that if we color the parent as white, then we have to contribute these many nodes to black. And if we color this as black, then we have to contribute these many nodes to white. This will actually help us in arranging the nodes black or white. For example, at level 1, we have node 1. So we have one parent and 2 children. Similarly, at this level, we have one parent and 0 children for node 4. And for node 5, we have one parent and 2 children. We will use this to calculate our queries. Moving on to the solution. So now, up till now, to minimize the cost, we are using the technique that we can, for every node at odd level, we can assign either black or white. So let us say that we assign white. And for every node at odd level, even level, we are actually going to flip the color of its parent. So for example, this is white, then this will be black, and this will also be black. So the cost is 1 and now the cost is 0 and 0. So let us say for this is the odd level, hence we assign, let's say, black. And for this it will become white. The cost will be 1 and 0 and 0 respectively. Now the cost is actually equal to the number of nodes present at the odd level. And this is pretty much obvious because the cost is actually equal to 1 for every node at odd level, and for even it is always 0. So the cost is summation of nodes present at odd level. However, our main question is now to maximize the value of the tree, and value of the tree is defined as w minus b. To do this, we had defined a vector v, which basically tells us our contribution to black and white. This is defined for every node at odd level. So it is for this tree, it is equal to 1, 2 for node 1, 1, 0 for 4, and 1, 2 for 5. Now our goal is to maximize the difference between white and black node. So to do this, what we can do is we can choose the maximum from the pair and assign it, let's say, black. So we take the maximum and assign black to it, and we take the minimum and we assign white to it. And this is done for every pair. So what we are doing is basically, if we assign maximum to black, so let's say for this case, we assign the children to black, which is the maximum of the 2, then the node will be white. This is same as saying that we had colored the node white, because it does not matter at odd level what we do. This is an individual subproblem. So we assign white and the children will be black. So this will actually maximize the difference between the white and black node, and that would actually increase the answer of value. So our final answer can be 2 minus 1 plus, in this case we will assign the parent as, let's say, black. So we assign 1 minus 0 plus 1 minus 2, and we can take the mod value, and this is equal to 1 plus 1 plus 1 equals 3. Now if we go by this arrangement, then for the first node, for the first pair, we are actually assigning the 2, which is the number of children, as black. So this is okay. So we write black, and the reverse will be its parent. So this is white. For the second pair, which represents the node 4 with children 0, we assign max, which is parent to black. So this is also okay. So this will be black. For the last pair, we have 1, 2. The maximum is the number of children. So instead of white, we have actually assigned this as black to get the maximum value. So this is black, and this is white. Now you can check that the cost is actually minimum, which is equal to the number of odd nodes equal to 3. But now the value has been maximized. The value is now equal to 3. Moving on to the second query, now we have to minimize the value. So in query 1, to find the maximum, we just assign the maximum of each pair to black and minimum to white, and this actually increased our answer. For this, let us say that we create from V a difference array, and this is basically the absolute difference of these pairs. So for example, for this tree, it is equal to 1, 1 and 1. For maximum, we just added all these and got our maximum. This is true because we are only concerned with the number of white node and black node. And if let us say that this one contributes to white, this means that we had actually contributed this two to white and this one to black. So we are only concerned with the difference, the absolute difference of each pair. So now we will work with this difference. Now to get the minimum value, we need to distribute these into two sets, which is white and black. Remember that distributing a number from the difference array into one set means that we actually distributed the maximum into the assigned set and the minimum to the other set. So basically our cost will always remain minimum. Basically, we can choose some subset of these numbers and give them to white, and the other will automatically go to black. We have to do this such that the number of white and the number of black, the absolute difference is minimum. Now there is no obvious greedy heuristic to do this. You can try some test cases and see that this is actually not possible using greedy. So we are going to use dynamic programming to solve this. Now our initial problem has been transformed to the following problem. We are given an array diff from d1 till dk, and we need to choose some subset such that the sum of the subset chosen and the sum of the subset left, the absolute difference between them is minimum. For example, let us say we choose the subset S as d of k1, d of k2, and so on. Then our answer, which is the minimum value, is actually equal to summation diff minus summation S. This is basically what is left, and the difference from the chosen, which is summation S again. This is equal to summation diff minus 2 star summation S. We will calculate this subset sum S using dp. So let us define a variable m. Basically it is equal to summation of diff, the numbers that are initially present to us. Now let us define dp of I equals to 1 if there exists a subset S such that summation S equals I, else it is equal to 0. Basically, we store whether it is possible that some subset has a sum I or not. So now we have our base case. This is basically dp of 0 is 1. We can choose an empty subset whose sum is 0, and since it is possible, it is equal to 1. For a recursive case, let us say that for all values such that dp of I is 1, we have some x that has not been considered yet. So we can add that x into this subset of some I, and we can assign dp of I plus x equals 1. This x actually belongs to the difference array. Now to calculate our answer, we can iterate from I is equal to 0 to m and take the answer as minimum of answer comma m minus 2 star I. And since whether I is possible or not, this can be checked using dp of I. So we write a condition if dp of I equals 1. Only then do this. And we finally print our answer. Formally, we can write it as for all I from 0 to m and for all j from 0 to m, we can say that x is diff of j. And if j is greater than or equal to I, which means that it has not been considered yet, and dp of I, which means that subset with some I is possible, then in this case we assign dp of I plus x as 1. Now we can see that these m is actually proportional to order of n, because m represents the total cost which is proportional to order of n. Hence this is order of n square. Now n is 10 to the power 5, so we have 10 to the power 10 operations. So this will give you TLE because it is more than 1 or 2 seconds, which is given in the time limit. So now currently we are calculating dp values as we iterate over all the sum and we iterate over all the elements, and we try to add the current element into our previous subsets. So if previous can be calculated, signified by dp of I being 1, we initialize dp of I plus x also 1. So instead of storing our dp values into a vector, we are actually going to use a BitSet. So what is a BitSet? A BitSet basically is a data structure that only stores binary, which is 0 and 1s. The advantage is that today's compilers are either 64-bit and 32-bit. Basically, they process 64 bits parallelly, which means that for 64-bit, they actually take order 1 time. So if a BitSet is of size n, then the complexity that we achieve is n by 64. Or it can be n by 32, that will depend upon the compiler. Today's compilers are generally 64-bit. So in DP we are actually storing either 1 and 0 only. So BitSet is a perfect data structure for this. We can actually make a BitSet of size m. And now let us say in some point in our DP calculation, we have states like this. And x is equal to 2. So since this is 1, we need to make this one, and since this is 1, we need to make this one. To do this, we can see that we can actually use left shift and or to do this. For example, let us say that we had a binary number like this. So first we perform left shift by 2 because our x is equal to 2. So we get this. And now we take OR. So our final operation, the final answer that we get is this. And this is what was our required new state. Basically, we can write our transitions as dp is equal to dp or dp left shifted by x. So now our new complexity becomes order of n square by 64. The number of operations it will take is 1.5 into 10 to the power 8, which will pass our time limit. Now let us move on to another solution. This solution has been implemented by the problem setter and the tester. So basically we are given an array diff from d1 till d of k, and our problem is that we need to minimize summation diff minus 2 star summation s. Basically, we need to choose the subset S such that this is minimized. We begin by defining unique of diff. We basically remove all the repetitions from this diff array and we get u1, u2. Let's say there are L number of unique values. So now the main observation of this solution is that the number of unique values, which is L, this is actually bounded by order of root n, where n is the total number of nodes. So why is this true? This is true because the way how we calculated this difference. Now this difference of I is actually the absolute difference between the parent and the child, number of child for all nodes that are present at the odd level. The number of parent can be 1, hence this can be written as number of children minus 1. Now number of children is proportional to order of n, and since we only need unique values, the number of children can be like 1, 2, 3, 4 till L, and this summation has to be order of n. So this means that L is actually proportional to order of root n. We can use n into n minus 1 formula to get this, that L is proportional to order of root n. Now we create a map of frequency such that, let's say, u1 is present c1 times, u2 is present c2 times, and similarly u of I is present c of I times. We define our dp states as, we can define dp of I s as the number of occurrences of u of I such that sum is equal to s. Now we initialize dp of I comma s as minus 1. This is done for all I and for all s. Now we define our transitions. So if dp of I minus 1s is not equal to minus 1, which means that I minus 1s is possible, then we can simply write dp of is 0. Basically, since s is possible from I minus 1, we can actually add 0 occurrences of x of I, then we get dp of is as 0. And if dp of I s minus u of I is not equal to minus 1 and dp of I s minus u of I is less than c of I, that means that we can add one more occurrences of x of I. Then we basically initialize dp of I s as 1 plus dp of I s minus u of I. If both these conditions are not true, then we will assign dp of is as minus 1. Now to get our final answer, we will just iterate over dp of L and I. This is for all I from 0 to sum, and we calculate our answer as minimum of answer comma and sum minus 2 star I if dp of L of I is 1. So we have to add a condition that if dp of L I equals 1, only then we do this. So basically we can see that I is proportional to order of root n and s is proportional to order of n. So the complexity is n root n. Moving on to the code. So first I have processed the input for each test case. I take the input in the form of a tree using this variable which is defined above. It is defined as a vector of vector. Now I calculate this function dfs that will basically return me the absolute difference for every odd level. So basically I iterate over all the child, and if child is not equal to parent, which means that there are some children of the current node, then I increase this variable by 1 and call for all its children. Now if n children is 1, which means that the number of children of the current node is just 1, then this means that we are actually inserting 1 comma 1 into our variable v, which store our pair of number of children comma number of parent, and the contribution is actually 0 because 1 will go to white and 1 will go to black, hence we do not need to store it into our answer. Now if level is 1, which level and 1, which means that the current level is odd, so we push the n children minus 1 into our answer and we take the absolute value. This is n children minus 1 because there can be only one parent and n children is the number of children that we wanted. After calculating this, if query is 1, then we simply output the sum. Now I use this BitSet to calculate our DP. In base cases, DP of 0 is 1, and for every x in the difference, we calculate our transitions as first we left shift and then we perform the OR. Now our initial answer is the sum because this is the maximum that we can get, and we calculate the minimum as minimum of answer comma absolute value of sum minus 2 star I. This has been discussed before, and finally we print the answer. So guys, this is pretty much the whole code. Try to code it yourself, and if you face an issue, then come back and see it again. So guys, I hope you understood the problem clearly. If you have any questions, drop a comment in the comment section, like the video, and don't forget to subscribe to get our latest updates from CodeChef. Thank you and goodbye.